Good evening, students. Yes. So we'll start. So we had started with haloalkanes and haloarenes, right? So we were discussing haloalkanes and haloarenes. So in the first class, we have discussed what are haloalkanes, what are haloarenes, right? What is what is their general formula? How do you how do you what is the So what are halogen derivatives of alkanes? Okay, haloarenes are halogen derivatives of arenes. We have deal with their general formula. Okay, then ARX. So that is nothing but this represents your haloarenes. Then we have discussed about the nature of CX bond, right? We have discussed about nature of CX bond. Then we have discussed about the classifications, right? So base first was based on the number of halogen atoms. Next was based on the hybridization of carbon atom. Okay, compounds containing sp3-CX bond and compounds containing sp2-CX bond. Then we had discussed about the physical properties of haloalkanes. So we have deal with the boiling point, melting point, right? Then we started with, in the last class, we started with methods of preparations. So Groves process. Okay, then we are discussing the important methods of preparation that are the named reactions. Okay, so Groves process, then Darzan's process, then Markovnikov's rule. So what do you mean by Markovnikov's rule, right? So very important. What is Markovnikov rule? So alkene adds a molecule of hydrogen halide to form an alkyl halide. So whenever you have an unsymmetrical alkene, so the negative part, so negative, so the here the addition of unsymmetrical alkene takes place according to Markovnikov's rule. So we have discussed about Markovnikov rule. Then what is anti-Markovnikov rule? Anti-Markovnikov rule is a reverse of Markovnikov rules. Okay, so it takes place in addition of organic peroxide. So whenever you add peroxide, so anti-Markovnikov rule takes place. Okay, then what we have discussed, Finkelstein reactions. So Finkelstein reactions, then we have discussed about the Schwarz reaction. So in Finkelstein reactions, we are preparing the alkyl iodides. Okay, we are preparing alkyl iodides. And in Schwarz reaction, we are preparing alkyl fluorides from alkyl chlorides or alkyl bromides. Okay, then we have discussed about Wurtz reaction, very important reaction, Wurtz reaction. So here alkyl halide, it is treated with sodium in dry ether, giving you alkane, okay, plus sodium halide. So this is the Wurtz reaction. Then Sand-Meier's reaction. So Sand-Meier's reaction is basically a substitution reaction wherein you are going to synthesize a aryl halide. Okay, this is not for alkyl halide. This is for aryl halide. You can see here your product, right? So this is a aryl halide. So Sand-Meier's reaction is used for preparation of aryl halide. Then we have discussed about the Wood-Fittig reaction. So Wood-Fittig reaction is another reaction for aryl halides. So here you can see one aryl halide is taken and one alkyl halide is treated. It is treated with sodium. So coupling is made between sodium, the alkyl halide and aryl halide. Okay, in the presence of sodium, okay, and dry ether, you obtain a alkyl aryl halide. Okay, so this is a alkyl aryl. Okay, so this is another. So this is another reaction for preparation of your haloarene. Okay, so then we had discussed about what. So till here, yes. So in last class we have discussed in Wood-Fittig reaction. So now we'll start with nucleophilic substitution reaction. Now, what do you mean by nucleophilic substitution reaction? Substitution reaction means what? One of the atom is been replaced by another atom. So these are called as substitution reaction. Okay. So here nucleophilic substitution reaction. Okay, it is occurring in alkyl halides. Okay, so alkyl halides basically they form nucleophilic substitution reaction. So here two types of reaction we are going to discuss. One is nucleophilic unimolecular reaction, that is substitution nucleophilic unimolecular, and second is substitution nucleophilic bimolecular. So first we'll see what is nucleophilic substitution reactions. So nucleophilic substitution reactions, they are a class of reactions in which an electron-rich nucleophile will attack a positively charged electrophile to replace a leaving group. So here you can see this is a nucleophile which is electron-rich. Okay, so this is electron-rich. Okay, so this is electron-rich. So this is a Okay, so this is a nucleophile. So this is electron rich. So this will attack what? This will attack the positively charged electrophile. Okay, so here, so you can see here. So this is a product. So CNU plus X minus. So this will leave as a leaving group. So this is a nucleophilic substitution reaction. So always the electron-rich nucleophile will attack a positively charged electrophile to replace a leaving group. So these are nucleophilic substitution reactions. Okay. So, first, what did I say? Substitution, nucleophilic, unimolecular. So this is the first step what we are going to discuss. Now, what is substitution, nucleophilic, unimolecular? So such reactions, they follow what? They follow two-step mechanism. So this is called as substitution, nucleophilic, unimolecular reaction. So it is a two-step reaction. So this reaction is a two-step reaction. In the first step, the carbon halogen bond breaks heterolytically. Now, what do you mean this heterolytically? So when the cleavage, okay, when the breaking of bond takes place, whenever breaking of bond takes place, so it can occur by two types. One is homolytic cleavage. Another is heterolytic. Heterolytic. Okay, so whenever the breaking of bond, okay, breaking of bond takes place, so the bond can be broken by two types. One is homolytic, another is heterolytic. Now, first I'll give you the example for homolytic cleavage. Okay, homolytic means what? For example, H. So this is a hydrogen molecule. This is what? This is a hydrogen molecule. So I take example for hydrogen molecule. So hydrogen molecule can be represented like this. So whenever homolytic, so in this, always the homolytic cleavage, it takes place between the same atoms. Okay. So both the atoms are same. It is hydrogen. So bond, what will happen? The bond will break equally. So when the bond breaks, what will happen? Each bond will how many electrons are present between each bond, or between a bond how much electrons are shared? 2 electrons are shared. So this bond, when it breaks, so each hydrogen atom will take 1 electron. So this is homolytic cleavage. So always breaking of bond takes place when it is a same molecule. Between the same molecule, it will undergo homolytic cleavage. So equally the electrons are distributed. So this is homolytic cleavage. Now heterolytic cleavage always occurs in polar molecule. For example, HCl. Right. So Cl is a halogen. It is a halide. So highly. So if you compare the polarity, okay. So this is highly electronegative. Okay. So this is electronegative in nature. Right. So it is a electronegative atom. This atom, that is Cl, is highly electronegative in nature. So as a result, what it will do, it will tend to pull the electrons. Okay. It will tend to pull the electron towards itself. The electrons, the shared pair of electrons which are present between hydrogen and chlorine, it will tend to pull it towards itself. So as a result, what will happen? There will be partial positive charge and partial negative charge occurred on the, it will be appeared on the atoms. Okay. Then what will happen? So hydrogen, it will get a partial positive. This it will be, so this chlorine, when it is leaving, it will take the pair of electrons with it. So this will be Cl minus, and this will remain with no electrons. So it will have a partial, it will have a positive charge. So this will have a positive charge, this will have a negative charge. Why negative charge? It will carry the shared pair of electron with it, and it will leave. So what will happen? So in the first step, the carbon halogen bond is present. Carbon halogen bond is present. So as this is highly electronegative in nature, so there will be partial negative and partial positive charge. So the bond will break heterolytically. So the halogen retaining the previously shared pair of electron means what? This halogen will leave with the shared pair of electron. Clear? So this sentence is clear. So next, in second step, what will happen? In second step, the nucleophile. The nucleophile will react rapidly with the carbocation. Now this is forming a, this is a carbocation. You can see here. Okay, hydrogen with positive charge. Okay, or the carbon here, if when this halide, it will leave with negative charge, so carbon will be left with positive charge. So this is called as what? It is called as a carbocation. So this carbocation, as soon as the carbocation is formed, the nucleophile, the incoming nucleophile will attack this carbocation, okay, in the second step. So the nucleophile, this is a very fast step. So first step is a slow step, and the second step is a fast step. Okay, so these are the like this, the okay, just a second. So this reaction is always carried with what? This reaction is always carried in polar protic solvent. Okay, so this is the condition is what? It is carried in polar protic solvent, and such as, which are the polar protic solvents? Such as water, alcohol, okay, acetic acid. Okay, so what is present here? Polar protic solvent means there will be presence of hydrogen bonding, okay, between the solvent molecules. So water, alcohol, acetic acid, so they carry hydrogen bonding. So this reaction is always carried in polar protic solvent. So they will be having protons, okay, free protons are available, in all the conditions. So this reaction, SN1 reaction, it follows what? It follows first order kinetics. It follows first order kinetics. Is this clear? So what is nucleophilic substitution reaction? So in that, the first type is SN1, that is substitution nucleophilic unimolecular. So this is a two-step process. Okay. In the first step, what will happen? The carbon halogen bond breaks up heterolytically. Well, so I can just write it like this. So this is a carbon halogen bond. So this will break up heterolytically. So as a result, halogen will take its shared pair of electrons with it. Okay. And your carbon will be left with a carbocation. So it will form a carbocation. So what will happen in the second step? In second step, the nucleophile, which is electron rich, this will attack your carbocation. Okay, so this is your second step. So this reaction, how it is carried? It is carried in a polar protic solvent such as water, alcohol, acetic acid. So what reaction it follows? It follows a first order kinetics. Okay, so this much you need to remember. Now we'll see the reaction. So this is the reaction. Okay, so this is a reaction you can see here. So this is, what is the name? Can you tell me the name of this particular compound?
Tertiary butyl bromide.
Yes, it is tertiary butyl bromide. Okay, it is tertiary butyl bromide. Why it is called as tertiary? Because carbon is attached to three other carbon, right? CH3, CH3, CH3. So they are attached to other three alkyl groups. So because of this, it is tertiary nature. So tertiary butyl. Why butyl? 1, 2, 3, 4. 4 carbons are present. So butyl, and this is bromide. So this is a tertiary butyl bromide. So this is a conversion of tertiary butyl bromide to tertiary butyl alcohol. Okay. So it is carried in the polar protic solvent. So this is the solvent which is used here, water. So water, which is a nucleophile present, OH minus. So here in the first step, what is happening? This bond is broken up. So we'll see it in the stepwise. Okay, now you can see here. So this is the reaction. So here this is a reaction, main reaction, how it is carried. Okay, so starting reactant to product. So this is the main reaction. Okay, now we are going to see stepwise. So in the first step, the bond between carbon, okay, the bond between carbon and halogen will break due to the presence of okay, it is breaking. So due to the presence of a nucleophile and formation of carbocation takes place. So the bond which is between the carbon and halogen. So what is happening? Some bond is present between the carbon and halogen here. So it will break. Why? Due to the presence of the nucleophile and formation of carbocation takes place. So the first step, so this is what it is, the slowest and reversible step. Reversible means what? Again, you can get back your reactant. So step as a huge amount of energy is required to break the bond. So this is very slowest step. As I said, the first step is very slow step and it is a reversible step. So because large amount of energy you are using here for breaking the bond. So the bond is broken by solvation of the compound in a protic solvent. Thus, this step is slowest of all. So the rate of the reaction, it depends only on haloalkane and not on nucleophile. So the rate of the reaction, it depends only on the haloalkane and not on the nucleophile. Okay, so this is the first step. Then we will see the formation. So this is the first step. Okay, as I have discussed now, what is the first step? So this is a tertiary butyl bromide. Okay, your tertiary butyl bromide. So this tertiary butyl bromide, it is a very slow step. So what is happening? Heterolytically, this bond is broken. Okay, so this will take a partial negative charge. This will have partial positive charge. Okay, so when it is broken, what will happen? Carbon will be left with a positive charge. That is, it is forming a carbocation and this will have a negative charge, that is Br minus. Okay, so this is a first step what we are talking about. Okay, so this is carried out. Then we'll discuss the second step. Now what is second step? The nucleophile will attack the carbocation which is formed in the first step and a new compound is formed. Since the rate defining step of the reaction is the formation of carbocation, so hence greater the stability of formation of an intermediate carbocation, more is the ease of the compound undergoing substitution in nucleophilic, unimolecular or SN1 reaction. So in the case of alkyl halides, okay, in the case of alkyl halides, so in the case of alkyl halides, tertiary alkyl halides will undergo SN1 reaction very fast because of the high stability of tertiary carbocations. Okay, hence allylic and benzylic halides will show high reactivity towards the SN1 reaction. So this is about second step. So here what is happening? Here you can see the reaction. So this is the okay, so this is the attack of nucleophile. So in the first step, the carbocation which is formed. Okay, now what is happening? The nucleophile. This is a nucleophile which is formed from the first step, that is OH minus. So this OH minus will attack the carbocation which is formed from the first step and you get your product, that is your tertiary butyl alcohol. Okay, this is your product which is formed. So here the is, okay, here what is the second line? Just see. So the rate determining step of the reaction is the formation of carbocation. So the rate of the reaction, it depends only on the formation of carbocation. So what it is, so the greater the stability of formation of intermediate carbocation, more is the ease to form the compound. So in SN1 reaction, tertiary alkyl halides are more stable as compared to secondary as compared to primary. Okay, so tertiary alkyl halides, so when you are talking about stability, so tertiary alkyl halides are more stable than secondary and then the primary. Okay, so this is the this condition. Okay, so tertiary alkyl halides will undergo fast. Okay, so it will have a good product yield then as compared to secondary and primary. So hence allylic and benzylic halides will show high reactivity towards the SN1 reaction. So this is about your SN1 reaction. Okay. So next is SN2 reaction. So we'll go for SN2 reaction now. So what is SN2 reaction? Substitution, nucleophilic, bimolecular. Now here first one, it was unimolecular. Unimolecular, why? Because the rate of the reaction depends only on the substrate. Okay, rate of the reaction depends only on the substrate. So rate is directly proportional to substrate. So it shows first order kinetics because the rate depends only on one. Okay, one product. So that is substrate. So that is because of that it shows a first order kinetics. Okay, and so the rate depends on what? Rate depends on the stability of the carbocation. Now in the second, it is bimolecular. Why bimolecular? Because the rate depends on two. Okay, so this in this what happens? It is a one-step reaction. So the SN1 it will have two step, and SN2 is one-step reaction. So both the formation of carbocation and existing of halogen takes place simultaneously. So in the one step only, the formation of carbocation and leaving of the halogen takes place. Okay, so it undergoes via a transition state. So this reaction, it undergoes via a transition state. In the first SN1 mechanism, it shows racemization. Racemization means what? It will or it will be racemic in it will show maximum retention. Okay, and some this will be in inverse. Okay, but in this SN1 in this process, unlike the SN1 mechanism, here it shows inversion of configuration. In SN1, what happens? It shows completely retention. Retention means what? In your starting reactant, okay, how it was CH3, 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 Br, and your product was CH3, CH3, CH3 and OH. So this is retention, only your leaving group, okay, it is leaving, and your incoming nucleophile has been changed. Only this is the change. In SN2 mechanism, it shows complete inversion. Inversion means what? It will be reverse. Okay, since the reaction, it requires the approach of the nucleophile of the carbon which is bearing the leaving group. The presence of bulky substituents on or near the carbon atom has a dramatic inhibiting effect. So when you're talking about stability in this case, the primary alkyl halides are more stable as compared to secondary and tertiary. Now, in case of SN1 mechanism, tertiary are more stable, but your primary are more stable. If we take, suppose if we take tertiary alkyl halides, okay, if we take a tertiary alkyl halide, now first we'll see, then we'll discuss this point. Okay, first we'll see the reaction, then we'll discuss this point. So, so this is a one-step mechanism. So incoming nucleophile and outgoing. So incoming nucleophile and outgoing leaving group. Okay, so it will takes place in the via a transition state. So just see the reaction. So this is a reaction CH3Br plus OH minus giving you CH3OH plus Br minus. So what is the mechanism? So you can see this is a one-step reaction. So this is a reaction. Okay, now this is the mechanism. So this is OH minus. So this is your CH3Br. So CH3Br. Okay, so the nucleophile will attack from here. Okay, and the and your leaving group will leave. So leaving. So the what will happen? Nucleophile will attack from the backside, and your leaving group is leaving from here. So you can see it is undergoing a transition state in which carbon is having 5. You can see here carbon is having 5 valency. Okay, here the valency of the carbon is 5, which is unstable, which is unstable. So it is undergoing. So it is penta-coordinated carbon. Why penta-coordinated? Because it is bonded to 5 atoms. Okay, and which is unstable. So here what will happen as this making? So this is making of bond. Okay, making of bond, and this is breaking of bond. As this bond is been made up, okay, so simultaneously this bond will be broken. So breaking of bond and making of bond takes place simultaneously, and as a result this product is formed. So this is a product. Now can you see in the reactant side? Okay, see now in the reactant and in the product, is the compound appearing same? No. Okay, Now, if the umbrella is open like this, so here it is like this, right? So it is complete inversion. Okay, it is complete inversion. So if the bonds are here, now here the bonds are faced this side. So it is a complete inversion. So in this SN2 mechanism, it is bimolecular because the rate of the reaction, it depends upon the substrate as well as the leaving group. So rate of the reaction, it depends both on the substrate as well as the leaving group. So thus it will show a bimolecular or it follows a second order kinetics. It is following what? Second order kinetics. Why it is following second order kinetics? Because the rate of the reaction depends on the concentration of substrate as well as concentration of leaving group. Okay, so this is a SN2 mechanism. So making of bond and breaking of bond takes place simultaneously via a transition state. So what happens in SN1 mechanism? It shows retention, and in SN2 it shows inversion. Okay, so these are the SN1 and SN2 reactions. I hope this is clear. Yes, is it clear till here? Clear till here? Okay. So here the inversion which is occurring here, okay, this inversion is called as Walden inversion. Okay, remember the inversion of configuration here. Okay, this is called as Walden inversion. Walden. This is called as what? It is called as Walden inversion. Okay, Walden inversion. This inversion of configuration is known as Walden inversion. Okay, remember this. Now, yes, we were talking about the stability. Now, when we are talking here in SN1 reaction, what is the stability? Tertiary carbocations are more stable than secondary and then primary. In SN2 mechanism, primary is more stable, then secondary and then tertiary. Now you know that in SN2 mechanism, they have taken primary alkyl halides, and you know attack takes place simultaneously and breaking of bond takes place simultaneously. So both will go hand in hand. So now here, if I take here as there are primary, right? So here this is a primary alcohol because carbon is attached to hydrogen, not carbon. So this is a primary alcohol, alkyl halide. Now if I take a tertiary alkyl halide, CH3, no, I'll write it more clearer. Okay, so C. Okay, so this is what I've just represented this. I've written the complete structure. Okay, I've written the complete structure here. Okay, of this molecule only, I've written the complete structure. Now, suppose if I take a tertiary alcohol, now a tertiary alkyl halide. Now, what is our rule in SN2 mechanism? The attack of nucleophile will take place from where? It will take place from the rare carbon. So, rare carbon means from behind. Now, is it possible for the attack here? Can it attack this carbon? As you can see here, okay, there are only hydrogen atoms, okay, and there is free space here so that the attack takes place easily. Is there any free space here? No, right? So there is steric hindrance. There are bulkier groups attached to carbon atoms. So because of the bulkier group which are present on the carbon atom, the attack of this nucleophile will be very difficult. So attack of this nucleophile like this attack of the nucleophile, okay, attack of the nucleophile on the carbon is very difficult because of steric hindrance. Thus, tertiary carbocation is not stable here. Formation of tertiary carbocation is unstable, or we cannot take tertiary alkyl halides. Why? Because of steric hindrance. In primary, so there are primary will be more stable as compared to secondary and tertiary. So this is the stability in case of SN1 mechanism. Okay. Just a second. Okay, so this is about nucleophilic reaction SN1 and SN2. Now further, so stereochemistry we'll study after finishing this. Okay, first we'll complete the reactions part. So stereochemical aspect we'll see. So now this is a reaction of haloalkanes. Okay, so if you take a haloalkanes Rx, okay, and you react with NaOH or KOH, it gives you ROH. So this is a substitution reaction you can see here. So what is happening here? Okay, Rx is what? Alkyl halide you have taken, you are reacted with a base that is either a KOH or NaOH, it gives you alcohol. Okay, if you react with sodium iodide, if you react with what? If you react with sodium iodide, then what is the product form? It is alkyl iodide. Okay, if you react your alkyl halide with KCN, okay, if you react it with KCN, what it is the product form? RCN. What is RCN? It is cyanide. Okay, now when you react with KCN, now in this second step, one more reaction. If you react with AgCN, okay, now here if you react with KCN, what it was forming? Cyanide. It is forming what? It is forming cyanide. And if you react with AgCN, it is forming what? Isocyanide. Very important. Okay, you need to remember this. If it is reacting with KCN, that is your alkyl halide. If it reacts with KCN, what is KCN? Potassium cyanide. Okay, it is potassium cyanide. So if it reacts with potassium cyanide, it is forming cyanide. That is alkyl cyanide. And if it reacts with AgCN, okay, then what it is forming? It is forming isocyanide. Now, when KCN, why it is forming cyanide with KCN? Because KCN is ionic in nature. Okay, KCN is ionic in nature, and therefore both carbon and nitrogens are free to link with alkyl halides here. Okay, both carbon and nitrogen, they are free. They are free to link with alkyl halides. Since CC bond is relatively more stable than your CN bond. Okay, CC bond is more stable than your CN bond. So those C will get attached with the in this process. Okay, so cyanides are formed here. So here, what is the reason? KCN is ionic in nature, so therefore both carbon as well as nitrogen are free to link with the alkyl halides. But since CC bond is more stronger than your CN bond, okay, so what will happen? It will link to the carbon. So your alkyl halide, okay, alkyl group will attach to the carbon and it forms a cyanide. So cyanide will be alkyl, cyanide will be your main product. Now, when you're talking about AgCN, this AgCN, so this AgCN is covalent in nature. This is covalent in nature. So here, therefore, only nitrogen is available for linking. In this case, only nitrogen is available for linking. So AgCN, only nitrogen is available for linking. Hence, alkyl isocyanides are only formed. So what will happen when this Rx, it reacts with AgCN, only nitrogen is able to link, so it will form RNC. So alkyl isocyanides are the major products which are formed. Understood? So very important. Okay, why it is forming product? cyanide with KCN, and why it is forming isocyanate with AgCN. Remember this, very important. Okay. Then next is with KNO2. Okay, when it reacts with KNO2, it is forming, that is potassium nitrate. It is forming alkyl nitride. Okay. So this is a reagent, that is alkyl nitride. So these are some of the chemical properties of haloalkanes. Okay, how haloalkanes or alkyl halides, they react with different reagents. Okay, just clear. So we have deal with base. So this is NaOH or KOH as a base, then sodium iodide, KCN, AgCN. Okay, potassium nitrate. So it is forming, so this is the alkyl nitride. Then AgNO2, when it reacts with AgNO2, what it is forming? It is forming nitroalkanes. It is forming nitroalkanes. So nitroalkanes will be the product if you use AgNO2 as your reagent. Then Li, it is LiH. It is LiAl. Okay, it is lithium aluminum hydride. So they have written the LAH. So this is what it is: lithium aluminum hydride. Okay, lithium aluminum hydride, it forms what? It forms hydrocarbons. So if you take lithium aluminum hydride as your, so this is a reducing agent, right? So it will reduce it to hydrocarbons. So this is the reagent which is used. Then if you react it with ammonia, it is forming amines. It will form amines. Okay. Then if you react with Mg, okay, if you react with Mg, that is, it is a metal, it will form RMgX. RMgX is nothing but it is a Grignard reagent. It is organometallic compound, or it is Grignard reagent. Okay, so when you react with the metal alkyl halide, when you react with Grignard metal like Mg, it forms Grignard reagent. Then if you react with Na, okay, Na, it will form what? It will form alkanes. Okay, it will form alkanes. That is, if you react with metals, so it will form alkanes. Then if you react with sodium alkoxide, so this is the sodium So this is sodium alkoxide. Okay, if I take sodium alkoxide, that is NaOR dash, if I take, what it is forming? It is forming a ether, right? This is a ether. So this is formation of ether. So when you want to prepare ether, so you have to react your alkyl halides with sodium alkoxide. So when you react with sodium alkoxide, you will form your ether. Okay. Then when you react it with a ester group, okay, this is a ester salt. Okay, ester salt, you will get a ester. So these are some of the chemical reactions, or these are some of the reactions of haloalkane. So these are substitution reactions. So these are all nucleophilic substitution reactions. Okay, so these are various nucleophilic substitution reaction with various reagents. Okay, so these are various reagents. So taking any so many type of reagents, you can prepare your haloalkanes. Okay. So next is haloarenes or aryl halides. So what are the physical properties of aryl halides? Aryl halides are colorless liquid or colorless solids with characteristic odor. Okay. So these are colorless liquids or colorless solids with some good smell. Okay. They have some odor. They have some smell. Okay. Next, the boiling point, it generally increases with the so boiling point, it generally increases with the increase in the size of the alkyl group or halogen atom. Okay, so what will happen? So as you increase the size of the aryl group, so as the number of halogen atom increases, or the size of the aryl group increases, what will happen to boiling point? As in case of haloalkanes also, we have discussed this. So boiling point will go on increasing. Okay, so among the following So, you know, fluorine, then chlorine, then bromine, and then iodine. So, iodine is a having large size. So, the boiling point is will the order. So, aryl iodides will be having more boiling point as compared to aryl bromide, as compared to aryl chlorides and aryl fluorides. Okay. So, this is the generally the boiling point. So, generally boiling point they increase with the increase in the size of the aryl group or halogen atom. So this is about your boiling point. Then when we are talking about melting point, so the melting point of para isomers. So these are okay. So para isomer is more than ortho and meta isomer because of the symmetrical nature of para isomer. Now when you are talking about para, okay. So if you talk, this is ortho. So if I take this is ortho, okay, this is meta, and this is para. Okay, if I take a molecule here, OH, OH, and OH. Now you can see the melting point of para. So this is para, this is meta, and this is ortho. So they are saying that the melting point of this para is more as compared to ortho and meta isomer. Why? Because of symmetrical nature of para isomer. What do you mean by symmetrical? You can see if you put a center of symmetry here. Okay, if you put a mirror here, the molecule is symmetrical. Okay, the molecules is Cl right here. OH and CH3. Okay, so if you put a mirror here, what will happen? So it is having a center of symmetry. Here, if I put the mirror, here CH3 group is there, here no. Right, here if I put the mirror, here CH3 group is there, here no. So this is having a symmetry. So because of symmetrical nature, melting point of para isomer is more as compared to ortho and meta. Now, due to resonance in chlorobenzene, CCl bond is shorter and hence its dipole moment is less than chlorohexyl chloride. Okay, so due to the resonance in chlorobenzene, so due to the resonance in chlorobenzene, CCl bond is shorter and hence its dipole moment is less and that of cyclohexyl chloride. Okay, so this is another physical property of one of the aryl halides. Then what are the reasons? So why nucleophilic substitution reaction? So as compared to haloalkanes, aryl halides are very less reactive towards nucleophilic substitution reaction. Okay, so what are the reason? Okay, for their low reactivity, okay, for towards nucleophilic substitution reaction. So first is due to the resonance. So remember these 3 points, very important points. Okay, so due to the resonance, CX bond has partial double bond character. So this is the first reason why aryl halides are very less reactive towards the nucleophilic substitution reaction. So why? Due to the resonance. Okay, due to resonance, that is CX bond has partial double bond character. Second is stabilization of the molecule by delocalization of electron. So the whenever you're talking about aryl halides, so they will form stabilization. So there will be delocalization of electron, that is movement of electron will take place. So the molecules will undergo delocalization of electrons so that it will have the most stable form. Okay, to have a more stable form, the electron should undergo delocalization. There should be movement. Okay, so that so which is the what you say, which is the stable form. Okay, to see the stable form. Next is instability of phenyl carbocation. So the next reason for the attribution, okay, for the low reactivity is instability of phenyl carbocation. So the phenyl carbocation which is formed, it is unstable. So the instability is due to the phenyl carbocation. So however, aryl halides having electron withdrawing groups like NO2, SO3H at ortho and para position will undergo nucleophilic substitution reaction easily. So aryl halides, okay, aryl halides will not go nucleophilic substitution reaction. They will have low reactivity. But if you have at ortho position and para position, okay, with aryl halides, if you have NO2 group or SO3H group, then it will undergo a what you say, they will undergo nucleophilic substitution reaction very easily. Okay. So this is the example. So if you take chlorobenzene, okay, so this is a chlorobenzene, it is undergoing, so this is alkylation, Friedel-Crafts alkylation, and the second one is Friedel-Crafts acylation. Okay, so these are the two major and minor products. Okay, so this reaction, Friedel-Crafts reaction, it takes place in the presence of anhydrous AlCl3. So it undergoes in the presence of anhydrous AlCl3. Then second reaction is what? Second reaction is in the presence of this is a acyl halide. So this acyl halide in the presence of anhydrous AlCl3. So these are the two products. One is major product, another is a minor product. Okay. So these are some of the electrophilic substitution reaction. Okay. So these are some of the electrophilic substitution reaction. So electrophilic substitution reactions of haloarenes. So we'll see now the electrophilic substitution of reaction haloarenes. So the replacement, you know what is substitution reaction? So the replacement of an atom or a group of atoms through an electrophile. Okay. Now, before this, we have seen about nucleophilic substitution reaction. So as aryl halides, they have low reactivity towards the nucleophilic substitution reaction. So they will undergo electrophilic substitution reaction. So electrophilic substitution reaction means what? Instead of replacement of an atom or a group by nucleophile, here the replacement of an atom or a group of atom will take place through a electrophile. So it will undergo a electrophilic substitution reaction. So haloarenes, they will undergo some usual electrophilic reactions on the benzene ring, such as halogenation, nitration, sulfonation, and Friedel-Crafts alkylation. Okay, so these are some of the reaction which it will undergo. So here, so these are the various reactions. Okay, so these are electrophilic substitution reaction. So you can see here, so this is chlorobenzene. So chlorobenzene, when you react with Cl2 in the presence of anhydrous AlCl3, it will form what? The first product is 1,2-dichlorobenzene and the second product is 1,4-dichlorobenzene. So the first product which is formed, it is minor, and the second product which is formed, it is major. Okay, so always the para products will have a major product. Okay, and the ortho will be your minor product. So here, why it is a major product? Can anyone tell me why 1,4-dichlorobenzene is a major product and 1,2-dichlorobenzene is a minor product?
Para position and symmetric.
Para position is? Yes, anybody else? Why? 1,2-dichlorobenzene is having minor product and 1,4-dichlorobenzene will show major product. What you can see the arrangement of the atoms. Here the atoms are nearer to each other, right? So because of the steric hindrance, so due to the steric hindrance, it will have a minor product. Okay, and here the both the atoms, they are far away. Okay, you can see. Okay, so because of that, it will show a major product. Now the second is with concentrated HNO3, okay, and concentrated H2SO4. So this is, so the first reaction with Cl2, it is called as halogenation. Okay, this is halogenation reaction. The second is nitration. So it is undergoing nitration. So what is nitration or what is nitrating mixture? So always remember, what is nitrating mixture is your concentrated HNO3 and concentrated H2SO4. Okay, concentrated HNO3 and concentrated H2SO4, these are the nitrating mixture. Okay, so one will be your minor product and this will be your major product. Now this is what? This is 1-chloro-2-nitrobenzene. This is 1-chloro-4-nitrobenzene. Okay, so this is a major product. This is minor product. Why again? Due to steric hindrance, this will be a minor product. Okay, so this is nitration. So it will undergo a nitration. Next, when chlorobenzene, it is reactive with concentrated H2SO4. Okay, if you heat it with concentrated H2SO4, so this is sulfonation. What it is? It is sulfonation. So it will form products. This is orthochlorobenzene, sulfonic acid, and this is parachlorobenzene, sulfonic acid. Okay, so these are the reaction. Okay, so these are some of the electrophilic substitution reaction. Okay, so I think for today this will be more. Okay, so remaining part we'll see in the next class. So I'll just go through what all we have dealt today. Okay, so we have started with nucleophilic substitution reaction. So nucleophilic substitution reaction. Okay, so what is nucleophilic substitution reaction? So in nucleophilic substitution reaction, the nucleophile will attack the positively charged electrophile. Okay, and it will to replace the leaving group. So this is nucleophilic substitution reaction. Then next is there are two types. One is SN1 reaction, second is SN2 reaction. In SN1 reaction, it is substitution nucleophilic unimolecular reaction. Okay, so this is a two-step reaction. In first step, what will happen? The carbon halogen bond will break heterolytically. Okay, with the halogen atom, it will take the shared pair of electron along with it. Okay, and in the second step, what will happen? The nucleophile will react rapidly. Okay, and it will attack the positively charged carbocation which is formed from the first step. So here the polar protic solvents are used. What do you mean by polar protic? Protic means there will be availability of H plus ions. Okay. So which are the solvents? Water, alcohol, acetic acid. So these reaction, they follow what? They follow first order kinetics. Okay. They follow first order kinetics. Why they follow first order kinetics? Because the rate of the reaction depends upon the concentration of only substrate. Okay. Remember the rate of the reaction, it depends on only the concentration of substrate. So they are called as rate of, they follow first order kinetics. Okay. Then this is the reaction, main reaction. So what is happening here? We are converting our tertiary butyl bromide in the presence of a polar protic solvent like water to tertiary butyl alcohol. Okay. So this is the first step. What is the first step? The bond between the carbon and halogen, it will break. Why? Due to the presence of a nucleophile. So it will break how? It will break down heterolytically. So when it is breaking down heterolytically, the Br, that is your leaving group, will take the electron. It will take the shared pair of electron with it, and carbon will have a positive charge. Okay. So it will form a positive carbocation. There will be formation of carbocation. So this is very slow step. This is very slow step and it is a reversible step. Why it is a reversible step? Because huge amount of energy is required to break the bond. Okay. And this bond is broken by solvation of compound. How this bond can be broken? In the presence of a polar protic solvent. So this is very slow step. So the rate of the reaction, as I said, the rate of the reaction will depend on the concentration of substrate, okay, and not on the nucleophile. So the rate depends on only one. So it is a unimolecular. Unimolecular. Why it is unimolecular? Because rate of the reaction depends only on the substrate. Okay. So this is about SN1 reaction. Okay. So next, step 2. Step 2 is what? So in the first step, what is formed? Carbocation is formed. So the nucleophile. So first step is slow step. Now in the second step, what is happening? In second step, there is formation of carbocation. So the incoming nucleophile will directly attack this your carbocation and it will form the product. So this is very fast step. Okay, this is very fast step. Okay, so the rate of the reaction, it depends on the formation of carbocation. So greater the stability of formation of intermediate complex or the carbocation, more is the compound which is undergoing, more stable will be the product which is formed. That is in SN1 reaction. So tertiary carbocations are more stable than secondary and then the primary. Okay, so the so this is the about SN1 reaction. Okay, clear till SN1 reaction. Okay, so in the next class, from SN1, SN2, I'll just revise first, okay, and then we'll go for the further part. I think this is clear today. Yes, is it clear? Okay, okay then students, thank you. Have a good day. Okay, bye. We'll end the session here. Okay.